Okay, let's continue. Yeah, just to add a kind of simple summary about the needs of, the fact that we don't need to explicitly form our Q. So in practice, we don't even we don't even form our matrix F over here. So essentially, what we store in this series of this house order reflector is just this vector V, right? So once we obtain the vector V, and then we don't actually need to form this, but we just think of this multiplication result, and only using the vector V in this form, and then we can just compute the this corresponding result with the matrix Q1, Q2, and so on with the given vector or given column vector, right? So essentially, we just store the sequence of this V vectors, right? And this V vectors will have, like, if we started from the 10-dimensional vector, and then the first V is 10-dimensional, and the second V is 9-dimensional, and 8-dimensional, and so on. So the dimension of this V will become smaller and smaller that we need to store. And then you might wonder, like, what's the advantage or disadvantage of this QRD, the house order reflector, compared to the Gram-Schmidt process. Okay. So there are several pros and cons in practice. Although in principle they should give the exact same result, but they have a slightly different numerical properties, like when involving this small errors due to this floating point representation and so on. But I'll just skip that part. And also they will have a different computational complexity compared to the Gram-Schmidt process. But once you obtained this kind of pseudocode, and then you can at least compute the each line, computational complexity of each line. So for example, the first one is just selecting the corresponding column, so it doesn't need any computation in this case. We need to compute the L2 norm, right? So in this case, it requires the linear computational complexity, right? And then this part is the most significant computation. Then as you saw, once we obtain this V like this, of the vector along the first axis, right? The first dimensional axis, and then in order to do so, we need to compute this norm of that vector, right? And then once obtaining that vector, and then we just multiply it with this smaller matrix, right? Smaller matrix, and then subtract it from here. So the most expensive computation is over here, right? Vector V times the submatrix, and then again multiplying the vector V as a column vector, right? So you can follow these these computational complexity. Okay, and then let me move to another kind of interesting QR decomposition method, which is called the Gibbons rotation. And I think I explained it briefly before. So if you guys remember this, and starting from this two-dimensional rotation, then what if we want to perform high-dimensional rotation? I mean, this high dimensional rotation is a little bit difficult or tricky to think of, so we just think of like the two-dimensional rotation embedded in higher dimensional space. So in this case, as I mentioned last time, so given the three-dimensional vectors as this column vector, and then if we imagine the rotation only involving the first and the third dimension, okay, and then we just choose those two sub-dimensions and then form the two dimensions and then rotate them with the particular angle of theta, and then yeah, we just replace this guy, yeah, this guy with the corresponding dimension. Okay, so that is the simple idea of this. Just applying the two-dimensional rotation by only considering two of the entire dimensions. Okay. Okay, so in that case, how we embed or how we just perform this two-dimensional rotation in a higher dimensional space, and in that case, yeah, we thought of this kind of matrix, which is all kind of similar to embedding this F into the larger matrix, but in this case, we only embed like 2 by 2 matrix out of this higher dimensional space, but that is like if we selected like 3 and 8 dimensions, and then just two-dimensional rotation matrix of 2 by 2 matrix as like 3,3 and 3,8 and 8,3 and 8,8, right? So that's how we embed this two-dimensional rotation into here. Okay, so we use this simple property to perform this another type of a QR decomposition called Gibbons rotation-based QR decomposition. Okay. So here the main idea is almost simple. So given the matrix A of like having multiple columns, and then we want to convert it to the matrix R, which is an upper triangular matrix, and so the once applying this matrix Q, and then we want to make the first column as this kind of structure by introducing all the zeros except for the first dimension. So we perform this operation, I mean instead of the reflection, we perform this operation by using the Gibbons rotation, and so the idea is as follows. So in the case of two-dimensional space, using the house order reflector, we know that the reflected point is like this guy, right? And then we formed our vector v as simply the difference between these two vectors, right? So that's how we perform this reflection operation to change or transform this vector into this guy. But we can do the same job or same result by applying the two-dimensional rotation. And how we do it is as follows. So so if we have a 1, 2 as a two-dimensional vector, and then what is the rotation matrix that will produce some vector like this, and then because the rotation preserves the length of the vector, so the resulting vector should be exactly the same as the result of this reflector operator. So this times 1, 0 should be our result. Okay, or it can be like this guy. Okay. Okay, but now the transformation that we use to map this guy into this is the rotation, and rotation matrix can be defined as this, and then what will be our theta? Okay, what will be our theta? So we don't explicitly compute this theta, but we can at least compute this cosine theta and sine theta. So in general, x comma y and this guy is x squared and y squared, right? And this is an x and y, and cosine theta is this guy, and sine theta is this guy, right? And so we just plug that cosine and the sine theta in the place of this in our rotation matrix. Okay. So now, yeah, we at least know how to find this rotation matrix that maps some vector into like the vector that has non-zero at the first dimension, only at the first dimension. And then what if we do this? What if we embed this process or this rotation into higher dimensional space? So yeah, this is how we perform this in higher dimensional space than 2. So suppose this is our original matrix that we need to make into upper triangular matrix. So yeah, at the end we need this kind of matrix, right? And so yeah, let's just first take care of the first column, and then we now only need we are allowed to perform only like a 2-dimensional rotation, and that 2-dimensional rotation is first done by using those two values. Okay, so for example 1 2 3 4, suppose this is our original input column vector, and then we apply the Gibbons rotation for the third and the fourth dimension. Okay, so in this case, what will be the corresponding Gibbons rotation matrix? 1 1 1 1, and then yeah, in this case 3/5 is cosine theta, and sine theta is 4/5, right? And so it is rotating the third and the fourth dimension, and so we need to replace this sub matrix like 5/3 and 5/4, 4/5, something like this, right? So this is the matrix that performs the rotation only using this two-dimensional vector, right? So once it is applied, and then 3, 4 will be changed into 5, 0 due to this rotation. And then what other values change? What other values change from this input matrix? Because we apply this big matrix or this rotation matrix onto every column that we have. So although this matrix, rotation matrix, was determined by only looking at these two values, but when multiplying this with the entire, original matrix, then yeah, the upper part is remaining as the identity matrix and 0, and so the upper part will stay the same, right? And then those two was rotated as this 5, 0, and then when just multiplying it with the second column, and then this this two-dimensional vector will be also rotated, right? But that rotated vector will generate like some non-zero values over here. But this thicker X mark is indicating this value is different from this value, but they will in general be non-zero value. Okay, so after doing so, we now, so in this case, we want to obtain this guy, right? Non-zero value only at the first dimension and all 0 for the other dimensions, right? But in the case of Gibbons rotation, it can handle only the two dimensions at a time. So given this, we apply another Gibbons rotation by just multiplying another matrix onto this. Okay, and then now we focus on rotating those 2 dimensions. Okay, and then yeah, rotating these 2, we can also introduce these 0 over here, right? And then from the pattern of like how we embed this 2D rotation matrix into 4x4, yeah, 4x4 matrix, and then the first and the second column, sorry, the first and the fourth column will not change at all. So even though it was not written, it will be 0, but that 0 will be kind of staying the same. But the point is, we introduced this guy or changed it to this 0 over here, right? So we became kind of one step closer to this guy for this particular column of non-zero and 0, 0, 0. Okay, and then it's time to apply the Gibbons rotation. Yeah, on these 2 dimensions. Okay, so by using 3 Gibbons rotation matrix, and then we can achieve all 0 over here. Okay, and then now we obtained all 0 over here, and then it's time to move to the second column. Okay, so it's just like the bigger or outermost for loop, like iterating through each of our columns, right? So in this case, moving to the second column, and then yeah, we focus on this guy, yeah, this guy and this guy, and then using these 2 values, and then yeah, figure out this cosine theta and sine theta, and then introduce 0 over here, right? Okay, so this is the overall kind of process of this Gibbons rotation. So in this case, in general, it involves a much more number of computation, right? So it is approximately 50% more computations than the householder QR, and yeah, I mean rough or like the reason at a high level for this larger computation is because, yeah, so the purpose is still the same. So we are fully dense vector, and then we want to make it as this vector, right? And so in this case, how many how many matrix multiplication? So in this case, yeah, we needed the first and the second and the third, 3 different Gibbons rotation applied to this column to obtain this guy, right? Because we can only handle 2 dimensions at a time. So that way, if at a high level, it is almost the same as the previous householder case. So using A, so we apply Q1, Q2, and so on, and Q1 is playing the role of rotating this third and fourth, and the Q2 is second and the third, and so on, right? So overall, the number of these sequences will be much more than the householder one, because in the case of a householder, by using only one single matrix multiplication, we can just make this guy into this guy, right? Okay, so that's the that's the main reason for more additional computations of this Gibbons rotation. Okay, and then in this case, can we just imagine some other orders? So in this particular case, our purpose is still the same. We want to change it into this guy, right? Or it is achieved like over here, right? So in this case, we chose this guy and this guy, right? But what if we choose like second and fourth, and second and third? So in this case, we can still apply this QR, the house given rotation, right? So there are like different choices, that we can have in this given rotation. Okay, so in this case, so in general we can also choose this this particular order, 1, 4 and 1, 3 and 1, 2, right? So this is another alternative order that we can have. Any questions so far? So these are the two different methods to achieve this QRD composition. So here, one thing that we kind of ignored, or we actually need to check check one thing over here. So given matrix A, back to the house order stuff. So in this process, so we didn't kind of think of the fundamental question that we need to answer, which is like Q1 or this entire product of these matrices. Is this matrix really an orthogonal matrix? Right. So we considered reflection operation or transformation. Is it really orthogonal? And also, if we consider their product, will it also be still orthogonal, right? So in this case, so this is the, in general, the reflector matrix. And is it orthogonal matrix? How do we verify that this is a orthogonal matrix? So in that case, we want to verify that if this is Q, and then Q transpose Q should be identity matrix, right? And also, by definition, it is just a square matrix, right? And so, if it is satisfied, and then QQ transpose will also be identity matrix, right? Okay, so let's verify that simply. Okay, so in this case, it is I, and so first of all, applying this transpose to this identity matrix will not have any, will not change at all, and then this transpose will be applied over here, and then here, this is a scalar, and this is a kind of rank 1 outer product, and if we apply the transpose of this rank 1 outer product, and then they will be changing their order and then applying this transpose on each of them, and then it will produce the same result, right? So basically the transpose of the original matrix will have the same matrix, and then let's just multiply these two, then identity times this guy will have no effect, and so it can be written as it's like this. So 1 minus 2x squared, right? So like in this case, 1 minus 4x plus 4x squared, right? So I mean, it is analogous to this kind of computation because we have 1 over here, 2 over here, and some x over here. Okay, so so in this case, if we compute this cross term, and then it will be like this, right? And then we need to compute this 4 times x squared, right? So in this case, plus 4, which is the product between these two, and then V transpose V and VV transpose, and okay, so in this case, so it is not, so it is really the matrix product. So it's like V and V transpose and V and V transpose, and in this case V transpose V and V transpose V. Okay, so in this case, so we can compute this guy first, and so it is like computing this as a scalar, right? And this scalar can be, can cancel out the one of these two in the denominator, and then we know that this guy is denominator and the numerator is a VV transpose, right? So in this particular case, minus 4x plus 4x squared. So this is actually x. So minus 4x plus 4x will cancel out each other. So this part and this part will be the same, and thus we obtain this identity matrix, and thus this is the orthogonal matrix because it produced, Q transpose Q produced identity. Okay, and then the rotation, or this Gibbons rotation matrix that is embedded in some of these 2 dimensions, and and also each of these Q1 through Qn, if they are, each of them is orthogonal, and then the product will also be orthogonal. So Q1 transpose Q1 is identity, Q transpose Q2 transpose and Q2 is identity, and then if we just compute the let me just show only the 2 case. So this guy and Q2, Q1, and this will produce identity, and this is obvious because it will change the order, Q1 transpose, Q2 transpose, and each of our Q2 and Q1 is identity, and this will produce identity, and then this one produce identity. So the product of orthogonal matrix will also be orthogonal matrix, right? So the whole product will still remain as orthogonal matrix, and that's why we just satisfy the QR decomposition requirement that Q should be orthogonal matrix. And in the case of Gibbons rotation, the same scenario applies. So for example, in the case of 2-dimensional case, cosine theta and so should the negative sign be over here or over here? When rotating with the amount of angle theta, 어디 붙여요? 마이너스 어디에 붙여요? 둘 중에? 원래? 네? 위쪽? 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 Okay, so this is the rotation. Oh, yeah, and by the way, so this is the original rotation with the angle theta, and in the case of Gibbons rotation, so the original rotation should have the negative sign over here. Is it not the case? That is because, yeah, so in this rotation, to make some vector to the vector on the first axis, if the angle is theta, and then we actually need to rotate the angle of negative theta, right? So in that case, if this is correct, and then the typical, I mean, standard or original rotation with the angle of positive theta, we should have negative sign over here. 뭐가 맞죠? But anyways, yeah, let's assume this guy is put over here, and then because this guy is doing the rotation of the negative theta as an angle, so in that case, yes, so in this original case, yeah, the rotation with the angle of negative theta would put the negative theta over here, but in the case of cosine negative theta will be just the same as cosine theta, and sine negative theta will have like if it was originally positive, and then it will change the sign, right? So okay, so 오늘따라 이렇게 손가락이 안 먹네. 접지, 보통 이런 건 접지 문제인데 어디가 접지가 안 되는지 잘 모르겠네. Okay, so suppose this guy is our original matrix Q, and let's think of Q transpose Q. Okay, so in the case of Q transpose, it's actually interchanging between these two elements, right? And so as we saw in the previous example, if we just exchange those two values as a Q transpose, and let me just try to unplug this. So the problem is still here. Okay, it made the problem worse, so let me reconnect it. Okay. Okay, so in this case, Q transpose is exchanging between them, and then it is like this, and so it is equivalent to rotating the negative theta, right? So intuitively, like rotating theta and rotating negative theta will have no effect, which results in the identity matrix. And also, if we just compute this cosine theta and maybe it's negative sine theta, which is a transpose version. And then you can just simply check this. You can verify that it produces the identity matrix, right? And then if it is embedded in the higher dimensional space, like sine theta and sine theta, and maybe sine theta and cosine theta, and then its transpose version we'll have just exchange between these two, right? And so if we imagine their multiplication, and then for example like this guy and maybe this guy, that will produce also like if it is the same row and same column, then it will produce 1, and so it will still produce identity matrix. And so given the rotation, embedded in the higher dimension space like this, and then that is still an orthogonal matrix. And so, yeah. And so the product of whole sequence of these will also be identity matrix. I mean the orthogonal matrix. Okay, so that's it for this given rotation. Any questions so far? Okay, so now move to the next chapter of this least squares problem. Since you guys studied the least squares problem, this least squares problem in many different opportunities, I think we can just briefly cover this part. So you guys know that the least squares is like the minimizing this L2 difference, right? And then we understand this solution is the same as this guy. And then in this least squares problem, there are several different ways of obtaining the solution. Okay? So the first, we know this, I think, and then it can be solved in several different ways. And the first one is to use this normal equation. Okay, so the normal equation. So see. Give me 1 second. It's not responding. Okay, so this is the example that we used in the previous case, ax minus b, and then we want to minimize this. And in this case, the solution to minimize this guy, for example, arg min over with respect to x is the same as the solution is to solve this guy, right? So in this case, this is the normal equation, and A transpose A is just formed by this matrix multiplication, right? And then this is our A transpose B, right? And then once forming this linear system, and then it will be reduced to like this 3 by 3 matrix, and so this is A transpose A, and X and A transpose B will be like this, right? So the normal equation will always have the square matrix on the left. So in general, it will have the same number of equations and the same number of variables. And so in general, it will always give you the unique solution. In case this A transpose A is it is a non-singular or invariable. And how we solve this equation is through originally we can just think of the Gaussian elimination, right? So once forming this A transpose A, and then just applying the Gaussian elimination onto this matrix A transpose A and this B to obtain the solution, right? So this is the first way. And another way to solve this least squares problem is to, instead of forming this normal equation, similar, I mean, like what we saw in the previous lecture or previous lecture slide or chapter. So we can utilize the QR decomposition. Okay, so in this case, we just perform the QR decomposition on the original matrix A, and then as I mentioned, in this case, this guy is converted into this guy or this guy, though it's a little bit messy, but R times X, which is the upper triangular matrix, and then Q transpose B, which is our matrix. So in this case, what's the problem size? Once we apply this QR decomposition, so this is the R, X, and Q transpose B, and in this case, as I mentioned, the lower part, we have, we cannot do anything to fit this lower part, right? And so we can just obtain the submatrix on the upper part and the upper part of our vector B, and then solve for this upper triangular kind of linear system, which is a lot easier, than solving this guy, because in general, in this case, it will be just a full matrix like this, right? So in this case, we don't actually, we cannot just apply like simple back substitution, right? So in this case, we have to perform the full Gaussian elimination on this, right? Okay, so in the case of QR decomposition, I mean, the linear system to solve at the end should be much simpler, but which one, I mean, in this case, can we say that this approach is computationally more efficient than the previous one? It actually is not. I mean, in this case, the pre-processing step that we can view or that we can apply, I mean, this, which is our QR decomposition, is non-trivial, right? So QR decomposition has to go through like iterative processes, and so but on the other hand, in this case of a normal equation, and then although this one involves some computation, but that is simple matrix multiplication, and that's it, right? So we don't actually need to like iteratively update or compute some matrix in the middle or until obtaining R, right? And so in this case, the first step can be much cheaper in their computations, and then given this full matrix, and then it is a little bit, and let's see, and between these two methods of using this QR decomposition and and this and this and this normal equation based method, although I cannot give you like detailed explanation about why, but between these two, I mean, we sometimes think, let's think of some numerical kind of stability, like approximations. If the approximations are involved due to our floating point operation, and then which one will be better? I mean, which one is numerically more stable than the other? So it is just a rough explanation and idea, but in general, this normal equation may have a high chance of introducing more numerical errors. So this one is like a worse strategy than the QR decomposition based one in terms of their numerical stability. And I mean, rough reason is because so basically this A transpose A can be viewed as like squaring the given coefficients, right? So so if A was 1, 2, 3, 4, 5, and so on, and then to produce each of these values, we will of course perform the inner product between these two. Yeah, so between every columns, between every pair of columns that we have in our matrix A, so we will compute their inner product, right, to form this A transpose A. So in this case, yeah, in the original representation of an A, so if this was actually, yeah, the true value was 4.9 and this value was represented as 5, for example, due to our approximated representation in our computer, and then this 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 5 is yeah multiplied together, right? And so the error will be magnified. Okay, so the error existing in a single number in our matrix A, and then you can roughly view this A transpose A as a squaring the original input or original measurement, or sometimes it is the feature value, right? So in the case of least squares for our linear regression, and then this A is the set of like feature vectors of our data item, like feature by data instance matrix, right? So in this case, what if our measurement or the feature value involves a small error? So it should have been 5 or 4.9, and then it was measured as 5 due to some kind of computer or maybe some yeah, measurement device and so on. And then in this case, if we compute this A transpose A, and then this error will be like magnified because we are multiplying this already approximate or already inaccurate number twice, right? So that way this A transpose A, yeah, and this normal equation based method, although it's a cheaper, I mean, although it is a really simple method, but it has a drawback in terms of this numerical stability. So sometimes, yeah, sometimes, given the exact same problem, due to some numerical errors, like this method and this method gives a slightly different solution. And sometimes, yeah, the difference may be really like can be much bigger than we expected when those division by small number kind of thing is involved. Then I cannot give you like detailed example that contrast the difference between these two, but yeah, you can roughly have this kind of idea of this squaring may introduce a bigger error in our in our normal equation-based method. So it is cheap and convenient, but it has its own drawback. And compared to in contrast to this QR decomposition-based method, in this case we do not square. We don't have any steps of squaring the inaccurate values. So in general, this QR decomposition-based method will give you more accurate solution, or that is more robust to some numerical errors. Okay, and then the third method to solve this this least square problem is using the singular value decomposition. Okay, so in this least square solution, then we can view it as this guy. So we have some subspace which is our range of an A. So these are all the possible points spanned by our columns of matrix A, right? And then in general we are given B, which is outside of this span or range of an A, and then by carefully carefully choosing the linear combination coefficient of our columns of an A, and then we want to make it as close as possible to B, right? Okay, so yeah, when kind of deriving the normal equation and so on, and then we consider this kind of orthogonal projection, right, of this given B outside of our column space of an A onto the column space of an A, right? So this is our y hat, so or b hat. So this kind of error vector should be orthogonal to every column in our matrix A. So that's how we derived or proved this normal equation, right? So in this process, this y hat, which is guaranteed to be represented as A times x. So again, y hat is defined as the point, closest to point inside of our range of an A, right? So in that case, by that definition, we guarantee that this y hat is represented as A times x by using some vector x, right? So this vector x should exist, right? Okay, so from this perspective of this projection stuff, okay, so this y hat. So once we obtain the orthogonal projection, orthogonal basis or orthonormal basis of the same column space of this matrix A, okay, and then suppose this range is the span spanned by some u1 and u2 and maybe u3, which are all orthonormal. Okay, so in this case, how can we obtain this y hat? Or b hat, for example. Okay, so the orthogonal projection of B onto the column space of an A or range of an A, right? So in this case, so we have U over here. So U transpose U is the projection matrix, right? Of the given vector B. So in this case, so let me just remind you guys in case you don't remember. So you don't actually need to memorize this because it can be intuitively understood in this form. So U1, U2, and U3, and then U1, U2, and U3 transpose and B, right? So U1 transpose and B. So that is the part of computing the line segment, the length of the line segment, projecting B onto the line spanned by U1, right? And then once projecting that length, okay, and then U2, and then projected length and another projected length onto U3, and then that projected length is obtained by just simply computing the inner product with each of our orthonormal basis vector, and then they will be assigned as the linear combination coefficient with our basis vector of U1, U2, and U3, right? So that was it. So in this case, we can simply write this orthogonal projection into this form only when we are given orthonormal basis vector, right? Orthonormal basis vector. Okay, and then if we computed the SVD of our matrix A, okay, and then we can easily obtain the orthonormal basis vector of the column space of an A, right? So so if we just computed the SVD of this matrix A, and let's assume some reduced form, and then we will obtain U1, U2, and U3, and then diagonal matrix of our sigma, and V1 transpose, V2 transpose, V3 transpose. So this is U sigma V transpose, right? And so once obtaining or computing this SVD of matrix A, and then this part, our matrix U, will work as also normal basis of the column space of A, right? Yeah, that is simply because each column in our matrix A is now represented as the linear combination of these three, and then the linear combination coefficient computed from these two parts, right? And so, by definition, U1, U1, U2, U3 should be also normal, right? And then each of these three columns should be represented as a linear combination of these three. So, these three also normal vectors can work as the basis for the same column space of an A, or the same space spanned by these three original columns, right? Okay, and then the least square solution, once computing this singular value decomposition, and then the least square solution can be easily obtained. So computing this, right? And yeah, this U transpose times B, so that is what? So that is our coefficient, right? Coefficient with respect to the basis vector of U1, U2, and U3, right? And then okay, so yeah, in general, I mean the projection vector of U onto the column space of A will be to U transpose B, right? And then this is our B head, right? And then in this case, we need to compute this guy as, we need to represent this projection vector as the linear combination of original column of an A. So does it make sense? Okay, so back to this figure. So we can obtain this point by projecting B onto the column space whose also normal bases are matrix U, and so U transpose B is this point, right? But that's not the end of our story. So we need to be able to represent it as the original columns of an A, right? And their linear combination. Okay, so that corresponding linear combination coefficient will be our vector X. Okay, so in this case, yeah. So if A was originally decomposed into U sigma and V transpose, and then we can just plug A into this guy, right? And so by just comparing between these two, we can just make these two parts equal, right? So so more exactly here, we just multiply over here U transpose, for example, and U transpose, and then this guy will be gone, right? And so the resulting equation will be U transpose B should be like this guy, right? Okay, so we need one more step over here. One more step. Let's see. Okay, so yeah, once obtaining this equation, and then the next step will be like we obtained this vector, and yeah, we are kind of we have two matrices involved in this computation, but we don't directly compute this part first, but we actually obtain this x by using the two-stage process. So for example, this guy, okay, let's call this guy as y, okay, and then yeah, we are given some fully dense vector, and this sigma is some diagonal matrix, right? Some diagonal matrix, and then this y, yeah, this y is our variable to solve. And so, in the case of diagonal matrix, then yeah, we can just simply divide this. Yeah, if it is 1, 2, 3, and then we know this y is just simply the element-wise division by 1, 2, 3, right? So that way we can obtain this y, and yeah, using this a simple process, right? So once obtaining y, and then y is what? So y is this guy, right? Right? And then how can we obtain x in this case? So in general, we can, yeah, in general, yeah, we have a v1 and v2 and yeah, v3 transpose and our vector x, and we obtain the y over here from this diagonal kind of scaling or division. Okay, so once obtaining y, and then we can solve this equation. Okay. Okay, so here, yeah, how can we solve this vector x more easily? Just rather than solving this system in general by using the Gaussian elimination, and because we have our orthogonal matrix, right? Orthogonal matrix. So in this case, we have a matrix V transpose, and if we compute the if we multiply the matrix V on the left, and then this V transpose should be identity matrix. And so yeah, our vector x2 that we want to solve is represented as V times y. Right? So in this process, yeah, although it's a little bit messy, but once obtaining SVD, okay, and then the first step was to project or just multiply U transpose and B. Okay, so we obtained that vector, and that vector is corresponding to this part, right? And then to handle this diagonal matrix, we just diagonally scale each element or element-wise scaling on this vector by just dividing these values by our singular values, right? And then that vector is y, and then we need to obtain the vector x, and then this vector x is obtained as simply just this matrix is an orthogonal matrix, V transpose, and so we multiply V to make left-hand side as an identity matrix, and so x is represented as V times y, right? So this is the overall process. yeah, although it looks a little bit complicated and composed of multiple different steps, but in this case we didn't have any kind of linear, solving linear system, right? So all the steps are represented as a matrix vector multiplication and diagonal scaling, and also matrix vector multiplication, and that's it. So for these processes or steps, it doesn't involve any kind of complicated or computational intensive computations. Okay, so when using this SVD to solve this least squares problem, it has its own kind of pros and cons. So in this case, the pre-processing step can be corresponding to this computing the SVD, right? So in the case of QR, the first step was to compute QR, and then the next step was to solve the upper triangular system. And then in this case, we compute as a first step, we compute the SVD, and then the next step is, it is just a sequence of matrix vector multiplication and element-wise division, right? That's it. So in terms of the second step is the cheapest one in this particular case, but the first step is the most expensive one in this case, because computing the SVD involves much more computation than the QR decomposition, and also of course it's a much more computation than the simple matrix multiplication of A transpose A, right? So there are this kind of a trade-off between these two kind of steps, and personally, I'd like to point out that this SVD-based least squares problem solving is like a little bit of an overkill. Okay, so if you needed to compute the least square solution, and then you probably don't want to compute this SVD, because computing this SVD is a really expensive operation, right? And also it's like basically it's really an overkill. So you actually do much more computations of having to find out all the orthonormal bases for the column space and row space, right? And also those corresponding kind of matching relationship with respect to this diagonal kind of diagonal elements, like so just to remind you guys, eigen decomposition is to find out this particular vector v, right? And then in the case of singular value decomposition, we want to find out A times v is equal to lambda times or sigma times u, right? So this is the relationship that we want to find, right? So in this case, we want to have this a tuple of v and u and sigma, right? So in this case, all the tuples will have the orthonormal kind of vectors of v. This is the first tuple, and the second tuple is like v2 and u2 and sigma 2, right? So in this case, v1 and v2 should be orthogonal, right? And then this v1 should be mapped to u1, and v2 should be mapped to u2, and u1 and u2 should be orthogonal, right? So, and also they also involve this scaling vector of lambda 1 and lambda 2. So we need this kind of special kind of tuples that have this interesting relationship. So you can kind of intuitively think that finding out all these all these tuples existing in a given matrix is quite computationally heavy, right? So it's a little bit of yeah, rough kind of intuition at a high level, but yeah, it's like so if A is a 5 by 5 5 by 3 matrix, and then we consider like five orthonormal bases in the 5-dimensional space, and the 3 orthonormal bases in the 3-dimensional space. And so it's like in the 3-dimensional space, the orthonormal basis vector can be like, yeah, so starting from this standard basis vector, so any kind of vector by rotating these 3 vectors will still give you the orthonormal basis vector, because between each pair between these two, yeah, they have a 90-degree angle, right, having the length of one, right? But there are so many possibilities, right? And so also there are so many possibilities over here, right? And then somehow, yeah, I mean, in the case of 5-dimensional vector, we need 5 orthonormal vectors, but in terms of matching, we only consider like 3 orthonormal vectors, right? So given like this 5-dimensional space, we just ignore the last 2, and then we only consider the first 3, and then we have 3 orthonormal and 3 orthonormal vectors in a 2 different space of 5 and the 3-dimensional space, and then somehow while rotating these 2 sets of orthonormal vectors, and then at some point this particular vector is mapped to this particular vector, and this guy is mapped to this guy is mapped to this, right? Although they have some scaling differences, right? But at least orthonormal vectors are mapped to another set of orthonormal vectors in the target dimensional space, right? So, I mean, finding out these really like interesting matching relationship between 2 carefully chosen orthonormal vectors in the 2 different spaces. I mean, you can think of this as a little bit expensive, computationally expensive process. But anyways, that is kind of intuition behind this SVD. Okay. So once you find out that kind of set of tuples, and then that will reveal almost entire characteristic or property of the original matrix A. So that way, like SVD is a complete, completely revealing all the information existing in the matrix A. Although, it is a little bit rough and not very scientific explanation, but you can have some sense of this SVD in this manner. Okay, so in general, I'd like to mention that this SVD-based least squares problem, least square solving is not common one, because computing SVD may be much more computation intensive than the other 2 methods. Okay, so the time's up. So that's it for today. So okay, so we will meet next Wednesday.
교수님 잠깐 시간 되시나요?
네.
지난 월요일날 박인밥인데요.
네.
그게 그 증빙 서류 같은 걸 배달하시는데
네.
우선 저희 그 발표하는 과제가 여기 수업 듣는 학생이 두 명 들어가 있거든요. 그걸 어떻게 증명해 드리면 좋을지 잘 모르겠어요.
워크샵 타이틀이라 이렇게 오피셜리 동사무소에서 도장받아오고 이런 서류를 원한다면 그 워크샵이 이제 어떤 워크샵이고 이제 참여하고 있는 과제가 어떤 과제이고 그런 정도로 기술을 해서 워크샵 프로그램들은 아마도 거기 웹사이트나 이런 데 나올 거고요. 프로그램 입장. 그런 거를 이제 보내주면 될 것 같아요.
그리고 그 시험
왜냐하면 이게 또 어떤 기준이 없이 또 다 편의를 맞을 수는 없고, 이제 오피셜리 그때가 이제 시험 기간이거든요.
네,
그래서 좀 약간 좀 개인적으로 좀 바꾸는 게 좀 릴러턴트하긴 해요, 사실.
또 궁금한 게 시험을 바꾼다면은 전체 시험 기간을 전체 학생 집권 시험 바꾼다고 하지 아니면은
그걸 그렇게 바꿀 수는 없겠죠.
정말 따로 보는
이것
거죠.
때문에 다른 학생들 그렇죠. 미리 보는 시나리오가 될 것 같아요.
그럼 미리 보면은 막
네.
저희 연구실 학 5명이니까
네.
전날 화요일날 본다거나 이런 식으로
뭐 그러시면 될 것 같아요.
내일은 자세한 뭐 워크샵 관련된 서류들 자료들 적당히 줄여가지고
네.
메일 보내드리겠습니다.
그 화요일에는 가능해요? 보는 게? 그러면?
근데 일단 그래가 어제 메일 못 줬는데 그게 학생들 이야기 해보고 하느라
네.
거거든요.
네, 일단 화요일 그 전날에는 시험볼 수 있는 거죠, 그러면?
네.
네, 시험보고 보내주면 최대한 뭐
네, 감사합니다.
볼 수 있죠.
그 어떻게 가면 돼요? 교수님 행감 어제 보내주셨어요.